Very good morning, all. Today we'll be discussing about the types of motion of liquid and also the rate of flow of liquid in a capillary tube. So I think we have discussed in the last class about the viscosity of a liquid. We have explained more about the viscosity and the coefficient of viscosity. And now it's time for us to discuss about the types of motion of liquid. So now I'm just going to assume a pipe where a liquid is allowed to flow through the pipe. So at each point, the velocity of the liquid is going to be different. And after a particular time, the velocity of the liquid is going to be constant everywhere. So now, if the velocity of the liquid inside the pipe is, or else if the particle, each and every particle of the liquids exactly follows the path of the predecessor, then we call that kind of a flow as a streamline flow. Or if the velocity of the liquid is constant everywhere, we call that kind of a motion of liquid as a streamline motion. But what happens if the particle is not going to exactly follow the path of the predecessor? What happens if the particle follows a zigzag path? What happens if the velocity is not constant, right? So we call that as a turbulent motion. So in general, we have two different types of motions of liquid. One is streamline motion and another one is turbulent motion. In streamline motion, the velocity of the liquid is constant and each particle will exactly follow the path of the predecessor and the motion of the liquid will be in an orderly manner. And in the case of turbulent motion, the particle will not exactly follow the path of the predecessor. And also, the velocity is not going to be constant and the particle will follow the zigzag path, right? Or in other words, I can define the streamline motion as the motion in which the velocity of the liquid is below the critical velocity. We call that motion as a streamline motion. And the velocity of the liquid, if it is above the critical velocity, we call that as a turbulent motion. So now, let us discuss about the rate of flow of liquid in a capillary tube, which is nothing but a Poiseuille's formula. So now I'm just going to assume a water in a beaker, and at the end there is a capillary tube for the exit of water. And this capillary tube, it has length L, and at the radius of the capillary tube be A. And definitely there'll be some pressure gradient. There is going to be some pressure difference between the two ends of the capillary tube, and we call that as pressure gradient. And the coefficient of the viscosity of the liquid be eta. So now I just need to calculate the rate of flow of liquid in a capillary tube. And this is going to purely depends on the pressure gradient. Here it is given as P by L and the radius of capillary tube, which is nothing but A, and the coefficient of viscosity, which is eta. So V is nothing but the rate of flow of liquid. And this is going to be dependent on P by L, which is the pressure gradient, and A, let it be the radius of capillary tube, and eta be the coefficient of viscosity. Let this K be constant, right? And we have powers for the pressure gradient, which is X, A power Y, and eta power Z. So we need to find the value of this X, Y, and Z to find the rate of flow of liquid. So at first, I need to find the dimension of this rate of flow of liquid. So this holds the dimension V is equivalent to L cube T power minus 1. And now coming to the next part, which is P by L, which is pressure gradient, which is pressure by L. So the dimension for P by L is going to be capital L. Dimension of length of the capillary tube is going to be capital L. And for P, it is going to be M L power minus 1, T power minus 2. So altogether, this will be having M L power minus 2, T power minus 2. And next coming to, so far we have just given the dimension of V and P by L. Now we need to find the dimension of A, which is the radius of capillary tube, and the dimension of the coefficient of viscosity. So the dimension of the radius of capillary tube is going to be capital L. and the dimension of the coefficient of viscosity, which we have already discussed in the previous class. So which is nothing but ml power minus 1 t power minus 1. So now I just need to substitute the dimensional values here in this equation, right? B is equivalent to K into P by L power X, A power Y, eta power Z. So I just need to substitute all these dimensions. So instead, this is a formula. So instead of B, we have the dimension L cube power T power minus 1. And for time being, we just ignore K, right? Let us just keep this K aside. And P by L, the whole power X we have, right? The dimension of P by L is M L power minus 2, T power minus 2. So this is going to be M L power minus 2, T power minus 2. And we have X, P by L power X. So it is going to be M power X, L power minus 2X, and T power minus 2X. Similarly, now coming to A power Y. A holds the dimension of L. So this is going to be L power Y. And now it is eta power Z. And eta holds the dimension of M L power minus 1, T power minus 1. So this is going to be M power Z, L power minus Z, and T power minus Z. Fine. So now I'm just going to combine the powers of M, L, and T. So L cube T power minus 1 remains the same. The left-hand side is going to remain the same. And on the right-hand side, it is M power X I have, and I have M power Z. So I can just club it together, which is going to be M power X plus Z. And similarly, I have L power minus 2X plus Y and minus Z. So this is going to be L, Y, minus 2X from here, and minus Z. Similarly, T power, I have minus 2X and minus Z. So I have just taken minus out. It is 2X plus Z. So these are all the dimensions of P by L, A, and eta. We have just put everything together in the formula. So now what I'm going to do is I'm just going to equate the powers. So now what happens is we have an equation as X plus Z is equivalent to 0. So now I just need to equate, right? Equate the powers of this M, L, and T on both the right-hand side and left-hand side. I don't have M on the left-hand side, right? I don't have M on the left-hand side. So X plus Z is going to be 0. That is equation 1. And now coming to the second step. And for L, it is going to be Y minus 2X minus Z. Of course, I have L here on the left-hand side. So Y minus 2X minus Z is going to be equivalent to 3. Y minus 2X minus Z is going to be equivalent to 3. Similarly, I'm having minus 2X plus Z is equivalent to minus 1. So I can just write minus 2X plus Z is equivalent to minus 1. And then I have to simultaneously solve these three equations. We have three unknowns, which is X, Y, and Z. I just need to find the unknowns by solving the equations. So after solving these equations, I'm getting the value of X, Y, and Z as X is equivalent to 1, Y is equivalent to 4, and Z is equivalent to minus 1. So hope you remember we have ignored the value K because it's a constant. So now I'm just going to give the value of K as pi by 8. So now I just need to substitute the values of X, Y, Z, and pi by 8. X is 1. Keep this in your mind. Y is 4 and Z is equivalent to minus 1. K is pi by 8, and I'm just going to substitute everything together here in this formula. So I'll be having V is equivalent to, instead of K, I'll be having pi by 8. P by L, X is 1. So it is going to be P by L power 1. A power Y. A is nothing but 4. And eta is nothing but minus 1. Yes, because we have 1, 4, minus 1. So I'm just going to substitute everything together here in this formula. And that is nothing but pi by 8 is K. I'll be having B is equivalent to, instead of K, I have pi by 8. P by L power 1. So I have P by L. And A power Y. So it is A power 4. And then I have eta power Z, right? So it is minus eta. So I have just bring that down. It is A eta L. So this is the rate of flow of liquid in a capillary tube with the Poiseuille's formula. So at first, we need to find the factors which the rate of flow of liquid is going to depends on. So I'm just writing all the factors here. One is pressure gradient, another one is radius of capillary tube, another one is viscosity. Then the next step is we need to find the dimensions of all these factors. That is step 2. And then we need to substitute all the dimensions here in this equation. So, and then after substituting, I'm just going to equate the powers of, I'm just going to equate the dimensional powers. And after equating the dimensional powers, I'm just trying to solve these 3 equations and to find the value of x, y, and z. And finally, we are substituting all that in the formula of V, right? So this is the rate of flow of liquid in a capillary tube. So we can discuss the remaining topics in the next class. Thank you all.